Okay. Thank you for the introduction. So indeed, let's get this out of the way immediately. I'm not going to show you my own work for now. I'm going to show you some thing that I got interested in as on one of my scientific interests, but I didn't discover myself, which is a security bug in hardware which was called Meltdown. So the bug itself is very simple. So here's a very classical schema about rough model of a computer, like this one, for instance. On the very top, you have the hardware, something very raw that we can use to do various things. And the operating system, or OS for short, is a piece of software whose job is to isolate the hardware from whatever else you would do on this computer. You could run various software, Firefox, Thunderbird, whatever you like. And these pieces of software should not be able to access the hardware directly. They should ask first the operating system for the permission to do so. And therefore, the operating system is able to perform all kinds of security checks, so we don't destroy completely the hard drive just by doing for a bug or worse, an attack, for instance. The operating system, with the help of the hardware, does something else. It doesn't only isolate user processes from the hardware, it also isolates user processes from one another. So, for instance, if I'm running both Firefox to browse the web and Thunderbird to check my mail at the same time, they are not able to communicate except in very precise ways. So, in particular, this process, this software cannot spy on what this software is going to do. They are isolated. So more precisely, each of them has a piece of the computer memory just for its own usage. It cannot look at and even less write in pieces of memory that do not belong to them. And so this is called what we call process isolation. Processes are isolated from each other, and this isolation is, as I said, done by the operating system with the assistance of the hardware. We need hardware features to do this efficiently. And Meltdown is a bug in Intel CPUs that allow to bypass this isolation, so processes can actually spy on each other. Okay, I chose to talk about this security flaw in particular because when it was published in last January, it received lots of coverage with a bit of sensational titles. So I just picked two at the random, people claiming that you can steal passwords from users using this kind of security problems, that every modern processor has unfixable security flaws, you know, very worrisome and frightening titles. And so the first thing I want to say is this is mostly advertisement for that work. It's not that bad, and so there is a little bit of overreaction into all that we did, and I found that interesting. So I decided to get into the subject just to understand whether actually everybody's password will going to be leaked in the first few days or not, and actually not. So the thing is, almost any CPU manufactured by Intel after roughly 97 is vulnerable to the security flaws I'm going to describe. So that's a lot of machines. Whatever laptops, whatever servers, almost all of them use Intel CPU or something which is Intel compatible, but those are less subject to it. So mobile phones are mostly not affected, but still that's a huge amount of machines. Something else that was shocking is that this bug has existed for roughly 20 years before it was actually discovered, documented, and published. So people have suspicions that something was possible to exploit, but the actual code leaking memory while it was not supposed to leak was published only last January, so 20 years after the first vulnerable CPU were released in the market. And people were shocked because usually they take process isolation for granted. When you reason about the security of some computer or some computer system, you make the assumption that the hardware works the way you imagine it works. And this is why it's also a bit shocking that sometimes the hardware doesn't work the way it's supposed to do, because then it breaks a lot of assumptions that we do when we reason about security. So that's, in my opinion, the reason why we have lots of coverage with catastrophic titles in the news and everything, at least in the specialized news. But at the end of the day, basically any single user machine is probably fine. Okay, on my laptop I can spy on myself, great, but in the end it won't be extremely dangerous for me. The people who actually have problem are cloud computing providers. So those people have very large machines that they rent, but they don't rent you the actual physical machine. They create lots of virtual machines, and then they rent you computing time on one of these virtual machines. And what you could do with such a bug is to spy on other users which happen to share the same physical machine with you. You're supposed to be completely isolated of them, but you can still, for instance, try to get private cryptographic keys from their memories. If they are running some server with some authentication procedure that requires asymmetric cryptography, you can try to get certificates or stuff like that. But in a nutshell, if you're discovered about what I'm telling you here, you're fine, don't worry. However, I found it's a good opportunity to review how CPU work and a lot of their features which initially are used to make things faster and that we can abuse to bypass some security assumptions. And it's rather fun in the end. So, just a bit of timeline. As I mentioned, in the community there was suspicion that something could be done since 1905, more or less. But the actual research that led to this specific security problem called Meltdown was done and was finished in the late July 2017. At that moment, people who discovered, I will give the full names in a moment, but the people who discovered this chose to disclose the problem only to Intel itself, because it was the first entity concerned, and a few operating system vendors, Microsoft for Windows, probably Apple for macOS, and the main Linux kernel developers. So, in particular, the Linux kernel developers started to implement in software fixes to somehow mitigate problems of the hardware. Since Linux is open source, people started to notice that they were onto something. And in the end, Meltdown itself was made public in January 2018, so 3 or 4 months ago. In this paper, so once again, it's not one of my work, it's like Lips, Schwartz, Gruss, Pressure, Haas, Mengard, Kosher, Jenkins, Yarom, and Hamburg. That's a lot of people, because actually there were several different teams that independently discovered the bug, disclosed it to Intel, and then Intel made them in contact with each other so they could make a single group and publish the whole details jointly. All right, so before I can explain how we can bypass security implemented in hardware, I need to explain a little bit of how the hardware works initially. So there are two main areas of interest for today. The first is what memory looks like. So we're going to dive in the details of how memory, I'm talking about the RAM here, not the disk, but how the RAM is handled by modern hardware and specifically with Intel CPUs. And I'm going to give you the general ideas about how things work rather than the implementation details. Then when we understand how memory works, we also need to understand a little bit how a CPU, typically an Intel CPU, executes the instructions that we give to it. And then we will combine ingredients that we collected in these two sections to bypass what is called memory protection. All right, so that's a bit of work. Let's start with memory. So the standard model, especially if you're from theoretical computer science like me, how do you think about a computer? Well, memory is something like a huge array of integers, let's say 8-bit integers. An address is just an index somewhere in this huge array. And the CPU is a piece of circuitry that itself has a few memory cells called the registers, which can perform arithmetic, simple arithmetics on these registers, additions, divisions, standard things, and can also copy data from and to memory. So we can move data from registers to memory and back. And so that standard picture, I get data I need from the memory, perform calculation, put it back to memory. So that's nice when you do computability or even complexity theory, for instance, but the reality is a bit more complicated because modern CPUs offer translation mechanism. So the idea is that the code that is executed, I'm talking about machine language code, manipulate addresses, but doesn't manipulate address in physical memory. There is a layer of virtual memory, so this is just a virtual array which has some logical existence, but is nowhere located in the hardware, so it just exists in our minds, if you wish. And the CPU only manipulates directly this virtual memory. And then there is a map that translates address from this virtual memory into physical memory. So for instance, and the map is not necessarily linear, so we could have these first 4 blocks of virtual memory that happen to correspond to the 4 blocks here in physical memory. And the running programs have no idea about this. They're convinced they are going to write in the first memory cell, but then their translation occurs, and on the physical layer of the RAM circuit, it will be written in the 5th memory cell. And so this translation table is called a memory map. And actually, some part of the CPU takes care of the translation, a piece of circuitry called the MMU, Memory Management Units. And every time we make a read or a write to memory, then it translates the address to some physical memory. Just a detail, because vocabulary will be important. We do not translate address by address. Like, it's not possible to make a mapping just every single cell is mapped to any other single cell. Usually we map by blocks. We say the first 1,000 cells of virtual memory are going to map to these 1,000 cells of physical memory, because it's much simpler to just talk about blocks all the time instead of single addresses. And so what a block of mapped memory is what we call a page. So we say that the first page here is mapped to the second page here. That's just a block that translates. So, to make things simple, a page is just a block of memory. And the mapping can really be arbitrary. So here it's just a permutation, like I shuffle things around a little bit. But you can do whatever you want. In particular, nothing forbids you from mapping twice the same page of physical memory in 2 different places of virtual memory. So you could have 2 pieces of what appears to be the memory, which actually share the same physical space at the end of the day. So if you write something in this piece of memory, you will magically see it occur here, because it happens to be the same physical circuit in the end. There is no obligation to map all the memory. You could have some part of virtual memory which is mapped to nothing at all. It isn't backed by any physical memory. And so what happens if you try to read or write here will be explained in a moment, but we have no reason to do this. And actually it happens a lot, because suppose we have a 64-bit CPU, the number of cells in this virtual memory is 2 to the power 64. That's huge. That's much larger than any memory of any computer you could imagine. And therefore, there will be some parts of the virtual memory that we will not use at all, which is why it's manageable. So we can do really whatever we want in this memory mapping here. And okay, one piece of information, who decides this memory map here? Who chooses what page of virtual memory is backed by what page of physical memory? So for now, it's just the operating system. The operating system, one of its roles is to, at each moment, maintain a consistent map between virtual memory and physical memory. So it chooses who goes where. And the user processes, the things that run usually on the machine, are not able to change it. This is only the operating system domain. So it is a very useful feature for process isolation, what I mentioned initially. Because when we are about to run a piece of, I don't know, Firefox, for instance, we can remove from virtual memory everything that doesn't concern Firefox. We only map in virtual memory things that actually belong to Firefox or which are relevant to Firefox, and everything else is mapped to no page of virtual memory at all. And since Firefox has no idea that we are in a virtual memory environment, it thinks it's the real memory, it will think that it has the whole memory for itself and that nobody else is doing anything here. And it has no risk to overwrite memory of somebody else. And when it is time to switch the context and to, for instance, to run another software, then the operating system is going to demap all the memory belonging to Firefox and map memory belonging to this new process. And so like this, we isolate processes from each other. But actually, virtual memory is extremely useful for tons of other things. For instance, if you want to allocate a big array of memory, one problem usually is that, for instance, you want to allocate 1 gigabyte of memory. Without virtual memory, you will need to find a block of 1 gigabyte of continuous memory somewhere in the physical memory and give that to the process that asks, and to make it look like it's a proper array. But if you have virtual memory, what you can do instead is just find available memory wherever you can, and then you can map it cleverly to make it seem like it's a contiguous array of blocks. And so like this, you can deliver to application things that look like contiguous blocks of memories, and your C compiler is very happy, for instance. But in the end, you don't need to have this memory actually contiguous in the physical memory. So this makes things much simpler to allocate memory to processes, for instance. Everybody with me up so far? Okay. I also said, so it's not immediately relevant to Meltdown, but it's also important that we need to isolate not only processes from each other, but we also need to isolate a process from hardware. And I will explain a little bit how it works because it will motivate things later. So very roughly, and here I'm making a bit of a simplification, the CPU, typically an Intel CPU, can run in 2 modes that I choose to call the operating system mode and the process mode. They are not official names. Official names are numbers, 0 and 3, but this fixed the idea. We have 2 modes, OS and process. When CPU runs in OS mode, that's what happens when you boot your computer, for instance, it can access the hardware, whatever it likes, physically, and it can change the memory mapping, what we just saw before. And it can also shift to process mode, and in process mode, CPU forbids itself from accessing hardware and from changing memory map. And so this is in this mode that you will run all the software, normal software that you use. But at some point, even normal software needs to access the hardware. I mean, we want to draw something on the screen or access the network or do something like this. And so there is a special mechanism, system calls, so they're called. Your user process is going to put information in CPU registers, which is a request. So some integer encoding to say, I want to access this file on a disk, say, and run a special machine language instruction called syscall. And the effect of syscall is to shift to OS mode, which looks very dangerous because now I can do whatever I like, but immediately jumps to some function that has been designated by the operating system initially. So one of the first things operating system does when it wakes up, when you boot your computer, is to tell the CPU, I live here. I put some special code at this address, and if a syscall occurs, please jump to this address. And so this is an address which is controlled by the operating system and that the user processes have no chance to overwrite. So okay, now we are in OS mode, we are running some OS code, and the operating system does some work, like access the network, access the disk, whatever it likes, and writes the results of this calculation or this work back into registers, shifts back to process mode, and jumps back to the process who called us already. So it is somewhat like a function call, but a bit more complicated because we're changing CPU mode in the middle. Okay, now a bit of trickery. Here I went a bit fast when I said the operating system does some work. Potentially what happens here is very complicated, like we're accessing network, we're running device drivers to understand how to speak to such hardware. Clearly this step is going to need some memory. We cannot do this just with 5 registers or 10 registers. We're going to need to allocate memory. So typically what the operating system is going to do is going to map some memory for its own usage, then do the work with this memory, then unmap the memory because it's not needed and we don't want the user process to see it, and then proceed on writing the results and jumping back. So this step, OS does work, involves changing the memory mapping, even if in the end nobody notices it. And system call happen very often, so I already emphasized on it, file access, in inter-process communication, because yeah, one other thing. I said that processes were isolated from each other, but from time to time you actually want to communicate. Processes want to talk to each other for very good reasons. And so they do so basically through system calls. And so the OS checks that the communication is safe. So accessing the network is also system calls. Drawing on the screen involves system calls. Lots of things that you want to do very often. Imagine a video game, you want to do this kind of thing at least 50 times per second. So we want this to be fast, right? But it happens that changing the memory mapping is a rather slow operation. It's not extremely slow, but still you want to make it as fast as possible because it happens so often. Hmm? It depends on hardware. Let's say it's desirable to make it as fast as possible. And in Intel CPU, okay, it's not that bad, but people want to shave as much performance as possible. So they started to do something which looks a bit crazy, which is, okay, this memory that was needed by the operating system to do its work, why don't we leave it mapped somewhere in memory just in case we need it? And like this, when we do a system call, we don't need to change the memory mapping. We have this memory available somewhere. And so we save one step in the OS does works part of the previous slide. But of course, I talked about security a lot. If we actually do this, we break all the security model that I started to describe, because now our Firefox or whatever running is free to rewrite the operating system memory and to put crazy things inside. So if you have doubts about why Windows was very unsafe before 2006, this is essentially the reason. Because they did this, something similar to this, to be simple, and so processors were free to rewrite memory that shouldn't be rewritten by them, and so they could do crazy things. So we don't want this to happen. But still, we would like to do it because we want to make things fast. And virtual memory offers features to make this safe. Virtual memory offers access rights. So each page of virtual memory, roughly, has access bits. So it has one bit describing whether you're allowed to read in it or not, whether you're allowed to write in it or not, and whether you are allowed to execute code that is stored in it or not. So of course, whenever I refer to code, I refer to code written in machine language. So when you're in process mode, you have to obey these access bits. You cannot read a page which has a read bit set to 0. Operating system can do whatever it wants. It's just free party, it's the boss, so it can do whatever. It can also change the access bits for the same way it can change the memory mapping.
Access bit is a property of page.
Yes, each page has 3 access bits.
It's the same for all processes.
Yes, it's the same. But typically the operating system is going to change access bits before shifting to another process. Because to make sure that you don't read something you shouldn't. And execute, yeah?
It's stupid approach in general. It is a stupid approach in general because you have to change bits in all the pages.
Yeah, but or you can do this by batch. I'm skipping a lot of detail here about how you could do this eventually anyway, but the idea is that you're going to demap everything in the first place. Because here, what happens is that the operating system needs a bit of memory to run system calls. So you're going to map this memory somewhere and make it unreadable, unwritable, unexecutable. So the user process is just doing this job. If it tries to do something in this memory, it fails. But when you shift to operating system mode, since the operating system has the right to do everything, it can ignore these bits of reading, writing, and executing, and so it can use this memory for its purposes, and then jumps back to the user process. So now, without changing anything, we effectively saved the step of mapping in the memory belonging to the operating system. So this is what you can do with this mechanism. So this is how it works. This doesn't solve the problem of changing process, which is still a very complicated operation, but still for these purposes, it works. And so I said that it is forbidden to read or write or execute in a page that has unset bit of read, of write, or executing. But what happens if I try anyway? Because after all, I could try anyway. Well, in this case, the CPU detects the problem, of course, and jumps to some predefined function of the OS which handles the problem. So it's a bit the same. When the operating system, when the computer boots, the operating system tells the CPU, in case of a problem with access to memory, please jump to this function that I put in this space of memory, and which is, of course, impossible to write for user processes. So this is something fixed in advance, and then the operating system does what it wants to handle the problem. So this event is called a page fault or segmentation fault, and it is famous because the default behavior for Linux, and I think Windows probably, is just to kill the process. Like if you try to write or read in something you're not supposed to write or read, the response, what this function does, is just to terminate the offending process and do something else. So in the end, page fault happens somewhat like a system call, except that the program doesn't expect it, but it's an automatic jump to some foreign function. So this is very nice to save a bit of time, but we can also use it to our advantage. Something that I can...
First of all, we use page faults to working set modification.
To, excuse me, to?
Active working set. The set.
Yeah.
Well, the second level of memory can swap into RAM and nothing about copy and write and so on. Just straightforward way to use the memory mapping. Page fault is primarily used for transferring.
Yes, to swap in and swap out. Yes, I just wanted to avoid to talk about the disk at all. But yes, the primary, because I wanted to focus on memory, this is what we're going to be focused later. So okay, what he's talking about, let's mention it for everybody, is that you're all familiar with this swap mechanism. Like when you consume too much memory, like more memory than your physical device actually has, the operating system is going to use part of the hard drive, say, to store a bit more of memory. And in this case, we are going to, of course, if we do this, we should maintain the illusion that this memory is still in physical memory somehow. So what happens is that the operating system will decide, this page was not used for a very long time, I will put it on the hard drive, just one algorithm to decide, put it on the hard drive and mark it as forbidden to read and to write. And when some application tries to read this page anyway, the operating system will jump in this predefined function, realize the problem, and move the memory back in physical, from the disk to physical memory, and then the application has the illusion that it was in physical memory for the whole time, while actually it was stored temporarily on the hard drive in the middle. So this is actually, yes, like a lot of page faults that actually occur for this reason. My favorite usage of page faults is actually to make fork fast. So the fork system call is a system call where you should copy completely a process. You have a running process with all its memory and everything, and you want to make a clone of it. And maybe then the clone is going to do something else because it realizes it's a clone. But in the first place, we want two copies of the same process. It would be very expensive to copy all the memory pages physically belonging to one process to a new location. So what you do instead is that you give the same memory maps to the two processes, you mark those pages forbidden to write, and you only copy the pages that try to be written somewhere. So this means that the pages that are never written are effectively shared between the two clones of the process. And so this involves only memory and not disks. This is why I chose this example. So there are other tricks that you can use, but the idea is that there are many, many possibilities because effectively what happens is that you can choose more or less that if an application tries to read or write in this piece of memory, instead of reading or writing in this place of memory, please execute an arbitrary function instead. And so this opens many, many possibilities. You can do lots of illusions about memory with this. So we discussed two examples. This is not the point, so I will skip the other two. But okay, something, for instance, the Linux kernel did at some point was, okay, now we have this memory protection, we have these access bits, so I can map the memory that I use to treat system calls somewhere and it's safe. Why not map the whole physical memory somewhere? The physical memory is usually rather small compared to the virtual memory, we discussed this, and it could come in handy for various applications. So for some time, I think Windows as well, but Linux kernel mapped the whole physical memory somewhere in address space and marking it, of course, forbidden to read, write, and execute, and had some usage for this. But suppose now we have a bug which allows us to read a memory page in process mode, even if we're not supposed to, even if it's forbidden. This is the Meltdown bug. Basically, this is the security breach. Access bit, reading bit equals to 0 doesn't guarantee that your page is secret. So one important thing is that we cannot write. This security flaw says nothing about writing things at all. We can read things that we're not supposed to read. And so in this context, we could potentially read the whole physical memory, because if it's mapped here. Or at least we can read something belonging to the operating system. Like if we have device drivers for cryptography or things like that, it's still bad. Okay. So how do we do this? Now the other part of the talk is how do we do this? And to do so, we're going to discuss a little bit how Intel CPUs, at least, but we're going to do this in principle, executes instructions. So first thing is that to say things in a provoking way, machine language is compiled. When the CPU sees some instruction written in machine language, it doesn't execute it as a block. The first step is actually to compile it, but I should say to split it in simpler operations. There are many good reasons for this. It's extremely convenient for CPU designers, but I won't get into that. The point is that so we have these micro operations, which are invisible from the point of view even of the operating system. But that's what the CPU actually does. When the CPU receives an instruction, which is written in normal machine language, it splits it in a few micro operations that are completely internal to it, and then executes that.
Those micro operations, are they the same for Intel and AMD? Or
They are not even the same for several Intel CPUs, roughly.
So this compilation is
Yeah.
done at compile?
No. The CPU in hardware. It's a bit provoking to call that compilation because it's much simpler. It's just a substitution. But the idea is that if you want to make several CPUs that are compatible with each other, but with very different internals, your best strategy is actually to do this. Each of your different CPU will have very different micro operations, with some of them efficient, some of them inefficient, and then all of them will take the same machine language as an input, and internally are going to interpret it in different micro operations every time. So this is completely inside the CPU. Nobody sees it, not even the compiler writers.
It depends on technology.
For Intel, for what happens in Intel CPUs, sorry. Yes.
So it's below the level?
For Intel CPUs, yes. It's below assembly. And this is some compatibility device. Like this, you can maintain the illusion to your users that your CPU works the same.
Very deep,
Huh?
up to 100 steps.
Yeah?
Yeah? In risk.
I'm sorry.
Risk processors.
Yes.
Pipeline of one single instruction execution
Yeah.
can last for approximately 100 of main.
In very bad cases, yes. For modulus operation, it's 90, yes.
This compiler who is able to compile from machine instruction into micro instruction is a very complicated stuff.
Definitely yes.
It can be done statically, partially dynamically.
Yeah, it can change over time for sure.
But anyway, it is a very complicated problem.
Yes, indeed.
And in solution of this problem, there was a mistake.
Yes, a bit further actually. There is the problem is a bit ahead for this. I need micro operations, but the problem is not directly with the compilation process. It's just that we are going to need to look at the level of micro operations. So I introduce them, but the problem itself is a bit further. So I'm starting to build up things here. So a very imaginary example. So this is not something realistic at all, but just to fix the ideas. And this is relevant for what happens later. Suppose I want to read, I have some constant p, and I want to read memory cell number p in a register RAX, one of the registers of the CPU. So this could be compiled in an imaginary model, say an imaginary processor, to something like I actually get the value from memory, and I check by other means interrogating the MMU whether P is readable. If so, I copy the value that I had in RAX, and otherwise I make a call to this function that we discussed earlier that handle pages fault. So, and you see that this is more complex than this. So I insist that this is completely imaginary, just to fix your ideas, but this is an example of what could happen, and for instance, how you could use micro operations to handle the problem of checking that you have the right to read what you're reading. And this mental model is going to be enough to explain the problem. Now, these micro operations should be executed as fast as possible. So one classical way to do this is just to increase the CPU clock frequency. You do more operations per second. But still, each micro-operation is executed. If you execute each micro-op one at a time like this, somehow you're losing time. There are faster ways to do it, because each micro-operation itself can be divided into several steps. So it's not a compilation anymore, but it's just that first you should, let's say, parse the micro-operation that you have somehow internally. Then you should ensure that the data that you need is available somewhere. Well, they have like these several steps that are all, more or less all the same for all micro-operations. So what you could do in an ideal world is to start your instruction 0. I start counting at 0. You execute step 1, then you execute step 2, step 3, step 4, step 5. And here you immediately start executing step 1 of the next execution. And you do this in parallel. So you step 1 of instruction 0, then step 1 of instruction 1, and so on and so forth. And so like this, you have a better throughput. You execute more instructions in the same given amount of time. And the circuitry that is used to do the first step of executing an operation, for instance, is always in use. Because let's call this a parsing. Decoding would be the proper term. Decoding a micro-operation is the first step. Then the circuit that does this will do this for instruction 0, then immediately do this for instruction 1, then immediately do this for instruction 2, and you have no downtime like this. This is called pipeline in execution. You seem not convinced?
So what if this step 2 of instruction 0 collides with step 1 of instruction 1?
Yes, so this is exactly the question asked here, more or less. The idea is that what if instructions depend on each other? Right?
Well, and then instructions are done by CPU, so
yeah.
I expect it has a single thread. So
yes, it has.
So at every single point, it executes some one instruction.
That's not, and that's not quite true. Yes, but yes, but yes. Hmm? Yes. Okay. Once again,
processing units are regularly working parallel, and the pipeline should, while compiling the top-level instruction into micro instruction,
yeah,
will try to make a parallel program.
Yeah.
To utilize the execution unit in parallel.
Yeah.
So the huge issue of synchronization arises.
Yeah.
Well, and among micro instructions, to synchronize them, there are special commands.
Memory fences, yes.
5 ticks.
Yes.
And so on.
Yeah, right.
When the whole number of ticks is more than 100, for example, you can imagine that this compiler tends to begin the most complicated program for all those computer lifecycle. And in any case of this compiler, the processor will fail. It cannot execute instructions of the command set without compilation inside for a lower level. I see?
Yes.
In this architecture, we cannot put a line between hardware and software because hardware is implemented in software below it. And that is the source of the problem.
Yes, it is source of problems, of course, but.
So for any educated architect, it's an absolutely obvious problem.
Yes.
And this is the reason, by the way, for Elbrus processors being designed and implemented during 30 years. I'm sorry.
Go on. If you have interesting points.
I myself participated in 1990, about the time when this architecture was designed.
Yeah. Yes. Sure.
Why it was designed in Intel that way?
Yeah.
Let's tell you the story. In Institute of Precise Mechanics in Moscow, there was a team headed by Commissioner Babayan, who designed all the Elbrus architectures.
I'm going so you can.
Well,
yes.
Okay.
So the microphone
There was
can hear
Elbrus 1, Elbrus 2, Elbrus 3, and etc. They designed the high-level instruction set, and sometime in 19th, They tried to implement it in an element base like that. And they explained me and the other colleagues just the same architecture of the CPU. And I asked one of the designers of this architecture, his family name was Penkovsky. He was an author of Elbrus language, machine language, high-level machine language. I asked him the same question. I asked, it's obvious for me, I said, that this compiler, microcompiler, is the most complicated program, I expect that, for all the lifetime of this computer. It's huge, any bug in it crashes the CPU and so on. He tried to explain his point, but stopped and said, you are right. He just said to me, you are right. 1 week later, he went to the United States in Intel company and sent the message to the director of his institute telling that he will not return anymore. Some time later, Penkovsky became the main architect of Intel 386.
So the model of CPU we're talking about.
Some guy wrote even in Wikipedia that Pentium was named in his favor. Penkovsky. This is a joke, but
yes,
a joke is a part of truth. And we see this problem approximately at that time.
Yes. But discovered.
Nothing to be surprised.
Yeah. People were writing papers about this, like, not about exactly this attack, but we suspect that there is something
all the guys
for a long time.
In Moscow, they worked with Intel, more than 30 years ago. Elbrus microprocessor is implemented now, recently, in small form. When they was designed, it was huge. But now it's working, but it took 30 years to implement it. 30 years. One chip, 30 years. No surprise.
It's hugely complicated, yes.
Years, it became deprecated for 30 years.
Yeah.
Maybe with all this mistakes.
That we will see in the future. Yeah, no, but it's probably you should be here and me here, but still, it's interesting to have additional comments. But yeah, so the point, just for the next, for what I'm going to need for the rest of the presentation is that you're not executing a single instruction at a single point of time. You're executing several of them as much as possible. So if you can overlap instructions, even micro operations in your CPU, you're going to do it like this. If it's possible. Of course, they might be clashes. They might be clashes if I write code like this. Like if I do some computation, I store in place A, and immediately the next instruction, I need to use A. And so here, I cannot apply this model because I would need the result of this instruction to start this instruction. And so to deal with this problem that as I understand your initial question was, we have a yet more complicated piece of circuitry, which is part of what we discussed actually, where we try to parallelize it as much as possible. So the idea is that you have instruction, micro operations that you want to execute. They arrive like this, tons of them, many, and they are stored in first approximation in a queue here. Then we decide, is there an instruction here that we can execute? Like we have all the data that we need to execute it. Like I want to add 2 registers. Are the 2 registers ready? If they are, I send this micro operation to execute to what is called an execution port. For instance, the ALU, arithmetic and logic units, are a kind of execution ports. So the piece of circuitry that's able to actually do additions, subtractions, and this kind of stuff. You have several of them like this. In most CPUs, you have, let's say, 5 of different kinds. And so if one instruction is ready to be executed, it is sent to an execution port. It takes some time to execute, and once it's finished, we have the result, and the result is sent, say, in the register where we want to put it. And once we have done this, this triggers a scan of the queue, because now the registers have been updated, so we can scan the queue again to check whether there is some new microoperation that now becomes available. And so this is how we deal with the problem that some instructions need to wait from other to stop. So in a logical way, of course, the implementation details are much more deep, but the very high-level picture is like this.
Do you understand correctly that in previous picture, so essentially we have 4 ports rather than 3? Here, one, 3, no?
Yes, as a first approximation, yes. The problem is that you have different kind of ports for different kind of instructions, so it cannot be as clear as, yes. But if you want to get the picture, yes. And so this means that we can take some advance, like there is some instruction we are stalled because it takes a very long time to compute, but maybe we can start something which is after. And now we have another problem. If we try to do this, looks very nice, it's fast, it has incredibly complicated implementation, as we discussed, but you could have a problem with a branch. Suppose in your code you have an if then else. Looks innocent, but now I cannot just tell reliably what is the next instruction, because in this picture I just assume that instructions that we want to execute keep coming like this. But here we have a branch, we don't know if the next instruction is going to be a then or it's going to be an else. And the solution to this, so once again I'm going very roughly, you might want to add details later. The solution is we make a guess. So there is a very complicated piece of circuitry today that tries to guess its best what is going to be the answer, are we going to be left or going to be right, and then starts to execute initially one of these branches. And if we realize that we were wrong, then we cancel everything that we did and we go on the other branch. So roughly speaking, oops, excuse me, we are here, we make a prediction, we are going to go in the then part, we start to send instructions to the execution port, and to make things simple, and a very good case, we realize that we were wrong. We predicted then, but it was else. So what happens is that all these calculations that we were doing in this execution ports are cancelled. We never send the results to the registers. We say that the instructions are never committed or retired. So I'm going to be, so you can be heard.
Again, this is more complicated.
Of course.
Because 2 branches are, the scheduler or microinstructor tries to execute 2 branches in parallel.
So yes, you can even do this.
Buffers, and when it became clear which branch is true,
it cancels the others. Yes. Okay. So okay, it's great. What I wanted to simplify out of clearness, you get the full details. So experts are not bored. That's good. So yeah, indeed, we can try both in parallel and cancel whichever we want. But the whole point of all this is that execution of a single machine language instruction is complicated like hell, and that we are executing several of them at the same time, that we're executing some of them in advance, and even sometimes even canceling what we tried to start and everything. So once again, just an imaginary example, if you, just an innocent move like this, like you read something from memory, has a test here. Like you start to read from memory, then you test whether you had the right to do so, and if you had the right, everything goes, you copy your value in the appropriate register, otherwise you call a function. So, because of all that I described, the read, the actual fetch from memory, and the security check are somehow going to happen in parallel. And then, if the security check fails and we do something forbidden, we're going to cancel what we initially started. This is what triggered people, and this is what is going to make bad things happen. So that's now the part where we actually hack something by exploiting caches. So here I even make it clear that there is a simplification so we can get more details. But initially, accessing memory is somehow slow. Once again, what you think is memory, even with virtual memory, is more complicated. When you have to access a cell of virtual memory, it is somehow slow, even for the RAM, compared to CPU registers, for instance. So you have small pieces of memory very close to the CPU, actually inside the CPU, called caches, in which you remember the values of the cells you recently accessed. So the assumption is that if you access something, probably you're going to access it again soon. So you keep it in some cache, and therefore next time, instead of going far in the RAM to get it, you are only going to watch the cache. This leads infinite amount of problems when you have several things running in parallel because it breaks any kind of synchronization, but that's not my point. My point is that when you access something twice, the second time it's much faster to access, be it being a read or a write, and supposing you have only one thread. Because of what I explained, you remember when we read something, first we fetch it from memory, and then in parallel, we try to test whether it's forbidden or not. But by the time we realize it was forbidden, still, okay, we will never see the value that was forbidden, but this value is loaded in the cache anyway, and the cache is not going to be flushed. And this is what is going to be bad. Second thing, we can test if a given memory cell is in the cache or not. That's very easy. Try to read it, even if it's forbidden, you don't care. And time, how long it takes. If it takes a short time, then your cell was in cache. If it takes a rather long time, you have numbers about this, then the cell was not in cache. So now we have these two elements. When you make a forbidden read, you never see the value, but it is loaded in cache. That doesn't allow you to see it, because if you try to read it again, it will be in cache, but you will again get forbidden and get cancelled. But now you can test whether something is in cache or not by using a timer. And with these two ingredients, you can do something. So now is the bug, though this is the actual C. If you translate this in C, you get a working program that spy on virtual memory. So first thing you do, you allocate 256 memory pages somewhere, address A, say. So you just do a malloc, for instance, or something. So you have them here. You make sure that all these pages are not in the cache. You can do this by exhausting the cache. The cache is much smaller than the actual RAM, so you can force loading other things in the cache to guarantee that you have none of these 256 pages in your cache already. Yes, for simplicity, assuming that we're working on a page level, the caches are not quite working at the page level, but this will be good enough. So now we have 256 pages. They are all cold. None of them is in the cache. You try to read some forbidden address and store the result in some register Z. This is going to fail, but you have time. Immediately after, you try to do something. I put a print here, but do whatever you like, because it's going to fail anyway. Something at address A, so this address, plus Z times page size. Because of speculative execution and executing in parallel, you have time to start to do this. This will start to be done. But of course, at some point, the CPU is going to realize that, hey, this is forbidden. Don't do this. So at this point of time, we get a read error. But we got a read error. We still had time to load the page number Z out of our 256 somewhere in cache. So now, what we can do is, just using a timer, check which of the 256 pages is in the cache. We just try, for simplification. We try all of them, and we look at which one is faster to access. And this is going to be, the index of this page is going to be the contents of Z, because we started to access this page before realizing that we should not. So this is the main thing. So I want this to be clear. Feel free to ask questions now about this mechanism. No? Everything good? And it is so simple. Yeah, so there is more to this story. I'm just conveying the main idea here. But it's even warned here. But it can be made to work. So you have very impressive screenshots and video on Meltdown website where they show you that they have some graphical application here where they are typing some password and they are running in the terminal here basically this code written in C and with all the details managed. And so we can see here what they are typing because they are reading exactly the piece of memory that they, in which this is stored. So this is a laboratory condition examples. In real life, it would be much harder to actually achieve. I insist on that. If you can actually run code on your enemy's computer, there are much simpler ways to get secret information than doing this. But still, it's rather fun. However, nowadays, most operating systems implemented security fixes to mitigate this problem. So, if you're designing a new CPU, you can fix the problem rather easily. You just change the order in which you do things. You do not load things in cache before you're sure that you're actually going to read them. Since all the operations need to be completed before the read completes, you do not change the performance. You do the same things, you do them in a different order, and so you do loading in cache in the last, and that's enough. For older CPU, like for the CPU of this machine, not much can be done because I would need to change physically the CPU to do something, and that's rather hard to do. We could upload some new firmware, but that would be horribly complicated. On the software side, the first idea that was implemented a long time ago for other reasons is to randomize where you put things in virtual memory. Because what happened initially was that all the data were always loaded at the same place, at the same addresses in virtual memory. So if you wanted to spy on the operating system, you knew where it was. It was at address blah. So one patch was just to randomize the address, to load all this data at some unknown place. And since the search space is very big, it will take a long time if you need to explore 2 to the 64 bytes to find the information you're interested in. But there are yet more abuse that could allow you to predict where these things were loaded. So that could be another whole talk, so I won't get into this, but it was abused. It was abuse of a branch predictor this time. Okay. So another idea is just to do what seemed reasonable in the very beginning, that we map as little things as possible in memory. And so now, operating system actually maps in what it needs to do its work and then maps it out instead of having it ready. So it was the initial situation I described, where we had to put things in virtual memory and then out. And some operating system vendors made a bit unhappy claims explaining that this impacts performance in some workloads, even though in the worst cases they claim 17% slower execution of their benchmarks, most users were not complaining that much. So in practice of computing every day, it didn't change the world. So that's it. Well, some highlights of what I just discussed. So we are probably fine because that's just my laptop. I mean, I won't spy with each other processes. But the trick is really funny. The abusing that you can use in direction to do like exactly this. I found it immensely funny, so I had to show it to you guys actually. It was so cool. There were a bit of overreaction in the coverage. Like they were like, if this is going to be the end of the world and everything. I feel that researchers have a bit of pressure to, advertise their results, and the press has pressure to get clicks from viewers if you're reading online press. And so we could see this phenomena very well, because I'm not saying this is not a serious issue, it is. But for the random laptop users, it was probably not necessary to make some apocalyptic titles in the first place. And other things that we very well discussed that I wanted to emphasize is that CPUs are very complicated. And that our mental model I showed on the very first slide with just some arithmetic machine and a sequence of cells is nice to do, well, computability like I do, because, okay, this is what I like in the first place. But if you have to reason, for instance, about performance of intensive calculations or stuff like that, it takes a while to get used to all these data. And so, because, okay, I expected a bit more students to be here, and sometimes they write C code saying C is fast. C is fast if you can reason about all these things. If you write just C because it's fast without taking care of this, okay, it is fast, but not quite to the level of LAPACK, of heavy or other heavy calculation libraries or stuff like that. So once again, I'm merely a reporter here. All the credit goes to the authors who I will show the names once again because they deserve it. And thank you for your attention and coming here.